Thank you, Sally, for the kind introduction. It's such a pleasure to have a partner like Sally, who has laid the groundwork on what Stanford Energy is all about. So, as Sally pointed out in her opening remarks, it's quite clear that the world is changing. It's not just the United States, but many other countries. And a large part of the change that is happening is on the electricity grid. And what we like to make sure is that Stanford as a whole provides the value of helping the world change, not just in the electricity grid, but in all of energy. That's really our vision. So let me talk about the electricity grid, because this is going through some fundamental changes, probably unprecedented in its 120 years of history. It is called the greatest achievement, engineering achievement of the 20th century. And if you look at this electricity grid, this is, in the United States, the transmission network. You can think of this as the arteries and veins of the United States. If something gets choked up, the whole economy comes down. It's fundamental. But the electricity grid that we know today, of course, dates back to the times of Tesla and Edison, as Emery pointed out. And the architecture for the grid and how it is structured, the architecture has not fundamentally changed. The devices have changed, but the architecture is about the same. So this is the Tesla-Edison grid paradigm, as was mentioned earlier. You have centralized generation. So this is your centralized generation. Why centralized? Because it was cheaper in thermal power plants. You got long-distance, high-voltage transmission. And then you have medium voltage distribution in your neighborhoods. You have 13 kilovolts in your neighborhoods. And then you have 120 volts, 60 hertz in your homes. In this case, the generation always tracked the load. So if you turn on a light, somehow the generation understands that you have turned on the light, the load has gone up, and it'll ramp up the generation. How did they actually communicate with each other? This is in the times of Tesla and Edison. How did they know? When you turned on the load, the frequency went down a little bit. And when the frequency went down, you ramped up the generation to bring back the frequency to 60 hertz. And the standard in the United States is 60 hertz plus minus 0.035 hertz. That's how accurate it is. So that was the means of communicating at that time. The world has changed a little bit since then. So before we go into some of the changes that we are seeing, let me explain how the grid works a little bit more. Because based on this paradigm that I've just explained, the institutional structure, the regulatory framework, the business models also follows this paradigm. And so when that is questioned by some of the modern things that are happening, one has to look at it holistically. You can't just look at technology. You got to look at technology in the context of markets, in the context of institutions, in the context of the regulatory frameworks, which I'll come to. So this is how it works today. And very simple, I'll do a grid 101. Of course, there are much more details to it. Today, the grid, I'll just take the example of California, for example. There's a wholesale market which is run by the California Independent System Operator, CalISO, which is based in Folsom, which is just east of Sacramento. And they trade in wholesale electricity. There are buyers and sellers, and people sell the electricity. Utilities buy, utilities sell. Some of the utilities, some of them are large wind generators or solar, utility-scale solar plants. And that is governed because sometimes it crosses over state lines. It is governed by the Federal Energy Regulatory Commission, FERC, which follows the NERC rules, which is the technical arm of FERC. And it is a market, so there are prices that change, fluctuate. Not quite like a stock market. It is not real time, as I'll explain, but the prices are fluctuating at the wholesale level. And it is locational. Some places have lower prices than others because of congestion in the transmission network, et cetera. Then there's a retail side. And for example, locally, we are served by PG&E mostly. There are some other co-ops or munis around. And the retail side is local. And it is served, has to follow what I call the California Public Utility Commission. These are regulated utilities. And today, those rates of electricity are determined by the Utility Commission. And these are, for example, we have a very common tiered structure of rates that I and you and all us pay out here. This rate structure is now being changed in California to a more of a time of use rate, but that's the rate structure we had for many years. And what you really hope for is that the wholesale price is actually lower than the retail price. Because if that does not happen, the utilities will be buying high and selling low, which in fact did happen for a little while in California. But the rate structures and the wholesale price are determined in such a way that this is sort of hoped for. So that's where we are. This is how it operates. And frankly, if you go to California, the ISO, which I hope some of you get a chance to do, you'll have this big control room where the frequencies are monitored, and you're really looking at the whole California buying and selling. But there are many timescales involved in the grid. And I'll just explain a little bit what those timescales are. 16 milliseconds is 60 hertz, basically. And that's on the shorter timescale, and some things happen even shorter than that, like faults in the grid. And that the really long timescale is the asset planning, which happens over decades, and billions of dollars are at stake out here because there are new efficiency mandates or new kinds of power plants that people may be planning, or transmission lines, et cetera. Those are long-term planning. In between, there are various markets and things that the grid does. So how does the grid operate? Well, you have the legacy grid, and the first thing that the grid does is to forecast the load. And the load forecasting happens based on weather, some history, and that's mostly the day ahead. So today's electricity was planned yesterday, most of it. And based on that, the dispatch planning happens, and 90% of the dispatch is yesterday. That's the planning that happens. A little bit an hour ahead, so because the day ahead doesn't get the forecast exactly right, there's a little bit of a gap. So then you have a big knob, and then you have a little small knob called the hour ahead, and then finally you have frequency regulation, which is sort of on the second basis. That's how it works. Now, it's very hard to take wind, which is fluctuating on an hourly basis, trying to integrate onto this. This is the issue. And more recently, you have demand response, which is the peaks were going up, and they said, let's shave off the peaks by controlling the demand, because the buildings, for example, have some thermal mass in it. So you can turn off the air conditioners a little bit, and thereby shave the peaks, because that's a very cost-effective way of managing the total system-level cost. In fact, if those are grid geeks, look at how California ISO works on a daily basis. This was yesterday's load. And you see out there that the day-ahead demand forecast was off by the actual demand by about, sometimes in the middle of the day, by about a gigawatt. It's not trivial, by about a gigawatt. And then the hour-ahead forecast gets close to it, and then eventually is this fine-tuned, the really little knob, which is the frequency regulation. Okay, so that's how it's working. Given that what we have today and what Sally talked about early on, here are the big challenges. And this is not just California. I use California as an iconic example, but this is a global challenge. The big global challenges that we are talking about today for the electricity grid in particular is how can we help decarbonize our electricity system and reduce cost? And there are various measures. How do you decarbonize? Well, you can increase the efficiency, as Emery talked about. You can use nuclear, wind, solar, hydro, gas, geothermal. All of these are the options. Now, how you choose and what you choose has billions of dollars of implications. And each of these have different time scale. Nuclear is a longer time scale than, for example, solar. And so the planning for this becomes very, very important. But there's no doubt that the world is going to decarbonize and get more efficient. And the question is, how can we really help that happen? Second one is, how can we help make our electricity system more resilient and secure? And this is under various threats that come under, whether it's cybersecurity threats, as well as natural threats that happen because of storms, et cetera, that we have seen happen in the United States and, frankly, in the rest of the world as well. And finally, the other issue about electricity, which I think in the 21st century really ought to be a human right, because if you don't have electricity, you really don't get out of the stratum of society to really develop and have economic growth surrounding you. And that is, how do we offer solutions for access to affordable electricity? Because there are 1.5 billion people who do not have access to electricity. There's another billion or so who have very marginal access. And how do they leapfrog into the 21st century and don't have to rely on the wires coming there? Those are the big, big challenges that the world is facing. And we want to be right in the middle of that. So in terms of California, coming back to that, California just passed a Senate bill, 350, of getting to 50% renewable electricity by 2030. And this was 33% by 2020, 50% by 2030. Now, if you think about it, is it possible? Well, it is possible, but it's going to be hard. Because the grid, as we know it, was never designed for 50% renewable. And so the question is, how do we get there? So just to give you an idea of what's the lowest cost way. Well, for example, if you're looking at wind electricity and solar electricity, here are some numbers. This is data in power purchase agreement, PPAs, on price of electricity sold by wind. This is actual data from business contracts. And you can see right away that the price is coming down, and it is close to $20 a megawatt hour in some parts of the country. And this is using a $23 a megawatt hour production tax credit. And so if you take that $23 away, it's about $43 a megawatt hour, still pretty cheap. And where is today U.S. natural gas and China coal? It's there. U.S. coal and nuclear is over there today. Now, if you look at, because of that, you have the higher penetrations. Now it's sort of going up exponentially. A lot of wind capacity is being added. There's more added in China. But here you have about 65, 70 gigawatts of wind capacity, which is about 5 to 6%. At 5 to 6%, today's grid is fine. At 50%, it's a different ballgame that we're talking about. Solar is a similar story. The costs are coming down. These are actual business contract prices with the 30% investment tax credit, which will go down to 10% investment tax credit in 2017. But nevertheless, you can see the trends that are going, and you can see the PV penetration that are going up. People talk about batteries. Here are the actual prices of batteries. And right at the bottom is where Tesla and Nissan are. And they're at about $350 a kilowatt hour. But the trends are there. They're coming down. So if you think about the electricity grid now, and these are good trends. If you think about the electricity system in Tesla's and Edison's time, they did not have low-cost wind at scale. They certainly did not have solar photovoltaics, lithium-ion batteries, LED lighting, power electronics, computers, network distributed computing, the internet. They didn't have this. And by the way, they're getting cheaper and better. So if you think about the grid in the future, and you ask the question, what is the minimum cost of integration? Even if solar and wind were free, the cost of integration is non-zero. And that cost of integration at 50% renewable is non-trivial. And so these are the options. For example, if you have a grid, traditional grid, and if you were to add 50% of wind, for example, well, we know it is intermittent. It has to be balanced. How do we do that? Well, one option is maybe add generation capacity. Well, that costs money. If the generation capacity can, natural gas turbines can ramp up and down and keep up with the wind, well, that's one option, but that'll cost money. The other option is to put a lot of storage. How much of is necessary? Well, that's also going to cost money. And finally, you could control the load a little bit up and down, and thereby manage a little bit of the fluctuation of the generation. Well, that costs money too. The question is, what is the lowest cost option? What is the lowest minimum cost of integration of intermittent generation, which the grid was never planned for. And we really, frankly, don't know the answer to that. What is the minimum cost? So in Stanford, we are sort of looking at that very important problem and see how do we address that? What's the framework for asking that? And what are the options that we can provide? We're not running the grid, but what we could do at Stanford is provide technology, provide knowledge, provide people. So this is what we are thinking about. This is today's grid, and as we know, generation always tracks the load. Now you're injecting intermittent wind and some solar into it. How do we manage it? Well, maybe, can the load track the generation? And to do that, of course, you need some intelligence. You need a local brain. Those brains are cheap right now. And you can have a lot of distributed brains. This is, you can call it the Internet of Things. These are the things that I'm talking about, the grid-related things. But these are independent. And somewhere you need some coordination in that. And this is where some really cheap computing comes in, which is called the cloud today. And if you do that, you can perhaps do automatic generation control, which is done today, but connect it with what is going on at the edge of the grid, which is where the distributed resources are, and somehow coordinate and thereby minimize the cost. Now, of course, this is the technical realm that I'm talking about. This technology will only go somewhere when there are markets associated with it, when the institutions, where the regulatory framework is there, where the business models are created, to enable this to happen, and frankly, there are consumers involved because they are at the edge of the grid. So this is not just a technical problem. We have to think of it holistically, and that is the initiative that we are starting to create at Stanford, and what we are calling it, for lack of a better term, bits and watts. Watts have always enabled the bits. It's time that the bits enable the watts now. And that is what we are trying to create. Let me give you a few examples of some projects that we're thinking of. And let's start with the edge of the grid, and we'll sort of go towards the transmission system. Edge of the grid is where the loads are today. We have homes, we have buildings, we have factories, and that's where the loads are, and that so far, in the last 120 years, has only been the loads. Well, we're going to see some changes, as was pointed out, because the costs are coming down. So if you have the wholesale ISO market, then you have the electric utility, and then you have the edge of the grid where the loads are. Well, maybe you want a little router in there, just like we have internet router. But this is for the power. And this will be a combination of grid connect or network connectivity plus some power electronics to be able to turn on and off or modulate the power that is going in so that you can actually control the net load. And why the net load? Because you may have generation, you may have storage, you may have other kinds of loads that you may be able to turn off. Nest is a great example, but it is essentially a beautiful looking switch. That's what it is. And it is networked. And you may have other ways, other options in the future as well. And these have to this have to be networked, which most homes are, and most buildings are, and thereby be cloud connected. But one of the issues of the cloud is that there's some latency involved. Sometimes packets drop off, and there are delays that happen. So you can't rely entirely on the cloud. That would be a mistake. You still want the grid to be stable. And so you need some autonomous local intelligence to be able to do that. So this is a project that we have started called the PowerNet, which is really looking at the edge. Now, this is, it's not just, and of course consumers have to be involved. But now imagine it's not just one building, but a few buildings. Could you use that to provide services for the grid? So different homes and different buildings may have different kinds of loads. They may have storage, they may have generation, and you have the power router. And they have to be low cost. And the cost of this power router may have to comply with the market signals that are there, price signals. But you can then look at the cloud connectivity of an ensemble of this and thereby control the power and essentially in a cloud-based aggregation of these load and provide services for demand management as well as grid services for balancing the generation intermittency, et cetera. And so this is what is being done as we're just launching these projects right now. It's not that this is only in the future. There are some very nice work that has already been done at Stanford. This is some of the colleagues in electrical engineering, civil engineering, Ram Rajagopal, and many others. And this is a program called Wisdom. And here's the issue. If you look at the load profiles of the edge of the grid, where there's homes, people have been assuming the load profile looks like this, that you have a peak in the morning when people get up, then people go to work, the load comes down, and then it goes back up again when people come back home and start turning on the lights and start cooking and watching TV. And this is the load profile, and it's been the assumption. Well, what they did was they looked at the meter of 500,000 homes in this local area, and what they found is that many of the homes don't follow this way. In fact, they follow 200 different patterns. And what they found was some homes, the load is up at night and goes down in the middle of the day. Probably some grad students living in them. And so you suddenly find with data that this is not exactly what people thought it would be. And the question is that, can you predict the load of individual homes? It's very hard. It's very hard for individuals to know when people will turn on the lights and turn on the washing machine. But if you aggregate them, they will follow, the error bar goes down. The question is how much aggregation. And what they found was that if you just take a little bit of aggregation in a building, for example, or a feeder line, the error goes down to less than 10%. And so you really don't have to aggregate the whole city. And you can still be able to predict the load. And once you have the load profile, then you can start planning as to which edge of the grid homes and buildings are good for peak shaving, which ones are good for load shifting, and which ones are good for energy efficiency overall. And now you can customize the demand-side management, which really has not been done in the past. So this is something that we are embarking upon. There's some progress. In fact, all of this software will be open source. The beta has been released, and these are some of our partners, and this will be open source so that we just want to give it away so that people use it. That's the best way of making impact. This is not just software, there's hardware. If you are going to inject a lot of solar electricity or distributed generation onto the grid, you may have issues with how much backfeeding of electricity, the voltages may go up or down, and you need to measure, and thereby able to control. And so these are some simple devices that will latch on to your feeder lines and be able to measure and then be connected and thereby provide the information to be able to really manage it and manage the grid on the distribution level. This is a little bit of aggregation. And finally, there are grid spice level models where all the distribution things can go in to a grid spice going to the transmission level and thereby give you plans. Planning is supremely important for utilities and the ecosystem, because that's where billions of dollars are planned and deployed. So this is very, very important issues, and I'm just giving you snippets of what things are going on today, but this is just the start. The research program that we are planning is an integrated one. This cannot be just an engineering issue. This is a holistic thing. And so you go from all the way from appliances, smart appliances, et cetera, to power electronics, to controls, to optimization, all the way to market structures so that they are commercially viable, and frankly, with some security in mind, because the grid today is not very secure. This is not just a research program, this is an education program, again, offering holistic education to our students and our partners, not just in power system, but market structures, technology trends, et cetera. And this is not just for our students, but for our partners, as well as people in the industry and the government, so that they get the holistic view of what the electricity system is all about, and they can connect the dots and figure out which levers to push where to get to the decarbonization, the efficient grid. And so just to sort of summarize it, our mission is really to enable the industry and the electricity ecosystem. We don't run the grid, but we could enable. And to really cost-effectively and urgently achieve its decarbonization, efficiency, security, and reliability goals. The mechanism we have is to use research, education, and translation into practice. That's what we do. We're going to open source all our hardware designs and software solutions so that we enable people. And at the end of the day, we offer people. We educate people. Our success, we spent a lot of time defining what should be the success of bits and watts. And our success is really if the industry adopts and implements the solutions in practice. That's what we want to see. To provide the holistic education for our students and our industry and government partners and impact policy. It's very important. And finally, we hope, this is not the launch, we hope to launch with some real demos in early of 2016. So stay tuned. And finally, I just want to thank some of the early planning team that have really devoted a lot of time and effort, not only the faculty and some of our colleagues, but many students and postdocs have helped shape this, and some of the staff in Precourt have helped shape this. And this is in discussion and collaboration, some of our early partners. This is what is going on. And of course, we're going to open it up to everyone to participate. But this is sort of the early team that helped us plan this. So let me just stop here, and thank you very much. Happy to answer some questions. Okay. Okay. Emery.
Thank you. Some of us have been trying to quantify the cost of grid integration, and there are some surprises, like 2/3 of the world's non-hydro renewables turn out to be dispatchable rather than wind and PV, and there are huge benefits from properly diversifying the portfolio. But we found a huge gap in the literature, and I'm wondering if you're planning to fill it. Nobody seems to have assessed the cost of grid integration for big thermal stations, and such evidence as there is suggests it's a good deal bigger than for a diversified portfolio of variable renewables.
Great question. I think we're going to look at it as holistically as possible, including the grid integration from the distributed side, where if you generate electricity locally, you use it locally so that you may not need the full benefit of the transmission network. In fact, can avoid some congestion that may happen when you have very high peak loads. So we're going to look at it holistically. And frankly, I don't think anyone knows that answer yet. But what we can do is, and I'm sure you'll appreciate, this really depends on the region, where it is, the context. In California, it would be quite different from, for example, some parts of Malaysia. And so I think what we could offer is a framework of how to think about it, so that people locally can use their own context and own, geographical and other resources that they have to understand what the cost of integration is going to be.
Hi, Arun. Thanks again for, as always, a great talk. My question is actually very similar to Amory's. Have you ever, or have you made some efforts to think about what is a price or a value per megawatt hour of dispatchable, so that you can really put a value on the storage? Because everybody in the storage industry thinks about what do we need to make this at? What is our cost per megawatt hour? But what can you put a number value to the grid on the actual dispatchability versus?
That really depends on the service it's providing. If you're looking at frequency regulation, that's one kind of price, and it's frankly not megawatt hour, it's dollars per megawatt, because it's a power service that it's providing. On the other hand, if it's a load shifting, or if it's ramp following, there are different prices for them. So I think it really depends on the context. And I think batteries would be something that is used for frequency regulation is clearly going to be of different value than for load shifting. So I hate to give you a Washington-like answer, but it depends.
So are supercapacitors play at all for frequency regulation things as opposed to batteries? They can deliver power.
No, absolutely. So capacitors are already delivering, or VAR control, for example. If you have a lot of lag because of induction in the system, capacitors will provide the lead, and thereby.
Big shift, users. But I mean, literally in the grid, is there some thought that would be part of the solution?
Yeah, supercapacitor. Yeah, no, I understand. No, I think at the end of the day, if it's providing the frequency regulation, for example, it will compete with batteries in terms of dollars per megawatt. And if it is supercapacitors are cheaper and it has more cycle life, so the levelized cost versus upfront cost, I mean it has to be a candidate on that.
Hi, Craig Lewis with the Clean Coalition. We do a lot of work with utilities on redesigning the electric grid and really focus at the distribution level. Given that the distribution grid accounts for 2/3 of all of the capital expenditures in the electric grid, I'm always surprised when I don't see more emphasis on the utility business model to motivate the utilities to make the investments on utility side, energy storage, local renewables, et cetera, that are not behind the meter. So a lot of your focus was behind the meter, and just wondering why is that, and you know, how do you see a pathway to get the utilities to really accelerate this transition by changing the way they're making investments in the electric grid?
So I gave you just a glimpse of what's going on. In fact, it's not just behind the meter. It's on the distribution network, measuring on the feeder lines what the voltage and current and phase angles are to be able to make sure that the distribution network is stable. In fact, some of the problems that are going on in Hawaii are really in the distribution network. And when I look at the grid between the transmission system and the distribution, the challenges are really in the distribution system. Our transmission system is not so bad. In fact, we have the measurements now with PMUs, phasor measurement units. But we don't have those measurements in the distribution network. And in some of the utilities don't even know where the wires are. And so that's the situation. I mean, we have to look at that very carefully and help not only in the context of distributed generation and other kinds of assets, but also to make sure that they're actually stable and the cost of that is minimized, because that can be a very expensive proposition if the utilities start investing without thinking about it. And our job is to really to help them think through and how to minimize the cost and still be able to modernize the grid. One last. Okay.
Yeah, the industry seems to have different metrics for doing storage, and I would propose one that's dollars per kilowatt hour transferred. Right now, they talk about megawatts for 4 hours or dollars per kilowatt hour for batteries, but we need a standard metric, and if you do the dollars per kilowatt hour transferred, I think you're getting the whole regime in there.
Emery, you have a comment?
Well, a few days ago, Rocky Mountain Institute published a report on the economics of battery energy storage that pointed out that that value is one of 13 values for behind-the-meter energy storage. Batteries and the 8 things they compete with all have many forms of value, so it may be difficult to capture very much using one metric.
No, I think I agree. I mean, it really depends on what you're using the battery for, as I was saying. If it's for power, regulation, frequency regulation, where you only care about the power, that's quite different if you're trying to load shift, which is megawatt hour transfer is really important then. That's it? Well, thank you very much.